Okay, good afternoon, everyone. I'm Andrés Rabuñal Gayo, and I work under the supervision of Jaume Navarro Caballé on the experimental characterization of electrodeless plasma thrusters for very low Earth orbit applications. My thesis falls inside the context of the air-breathing electric propulsion technologies that is right now a very important hot topic in the electric propulsion community because of the huge potential market that it would allow both in terms of civil applications and military applications, in terms of Earth observation, for example, or telecommunications, but also in the scientific domain, allowing, for example, for high-altitude atmospheric studies. So among of the many different studies that you can make, I focus my study in the thruster development, for which many different technologies have been proposed over the years, specifically Hall effect thrusters, but I focus on the helicon plasma thrusters, which consists basically of an injector through which you pour gas into the electric tube, and with a radio frequency antenna, you ionize that gas, and you accelerate it through a magnetic nozzle, and you create thrust with this process. So it has certain advantages in the sense that it doesn't need any cathode or neutralizer, so the power processing unit is very simplified, and it is less sensitive to erosion. That for me, that is the main strong point, because it makes it very versatile for the alternative propellants, and that's why it was proposed for that since the early 2000s. But on the other hand, it is a much less mature technology that suffers from lower efficiencies, and the physics are poorly understood. So just to give you an idea of the state of the art of the technology, the most efficient one was developed by Professor Takahashi from Tohoku University that has a 35% efficiency that for other technologies would be modest, but for this is astonishingly good. But we are working on that. So the context of my thesis is experimental. So in principle, was going to be divided between a plasma thruster breadboard model and a plasma source breadboard model, but we removed that part and everything was done in the thruster. So initially, I did a campaign with air, just the air of the laboratory, to then move to different air mixture gases, like nitrogen, oxygen, in different compositions, and the design of different diagnostics that I did a pilot probe that I presented last year. So I have just started my third year, and I can say that the tasks on the left, the experimental part has been completed or almost completed. Most of the post-processing has been done, but it is still pending consolidation and closure, but I'm working on that. So just to be on the same page, in last year's doctoral meetings, I presented the air campaign, and just the main takeaways that I want to give is that the thrust was below 1 millinewton, and I don't know if this is the pointer. Well, doesn't matter. And there's a specific point in mass flow at 13.5 SCCMs that the thrust saturates, and increasing further the flow doesn't provide thrust. And even at higher mass flows, the magnetic field can even penalize the thrust. And we laid the hypothesis, although we couldn't prove it, that this could destabilize the orbit if the mass flow increased further than that point. So from that campaign, two questions arise. Okay, we have thrust. Can we do anything with this? And is the operation conditions that we tested representative of the orbit, specifically in terms of the air versus different gas compositions? And we identified two main problems related with the pressure required for the ignition, and that the uncertainties in the plume composition limited a lot the understanding of the performance. So the first thing I did was to develop an orbit propagation model that was validated against the GMAT and the different models that are in the literature with reasonably good results. That is modular, and for the atmospheric properties uses the NRAL MCC00 atmospheric model that passes a certain mass flow to two modules, one to compute the drag using gas surface interaction Maxwell collision models for molecular flows. And for the intake, I developed an analytical model, very simple, that was correlated with the literature and is reasonably good with a 30 to 20% relative error, but taking into account that these Monte Carlo simulations are very expensive, and this is so cheap that I can put it inside the loop and compute it at every iteration depending on the condition of the atmosphere. So it's quite okay. And then I compute the thrust with experimental results and propagate the orbit. So I don't want to go too deep into the details of the results, but I will say that the satellite lifetime can be expanded, and it confirmed our hypothesis of the orbit stabilization, but has two main problems. One related with the applicability of the assumptions that we did, because it requires highly optimistic gas-surface interactions that are theoretically possible, and people are working on that, but as of the current state of the art, is not feasible, and that we still assume that the performance with air was the same as with every composition. So to tackle that problem, I just took the atmospheric model and did a batch analysis of all possible compositions or conditions to find a possible operational envelope depending on the composition and the mass flow with two main hypotheses. First of all, I took one intake from the literature with standard values as of the state of the art, and we assume that atomic oxygen recombines in the intake mainly due to a surface chemistry, specifically due to associative wall recombination, that has been demonstrated to be a very important process for atomic oxygen. So it is a reasonable assumption and makes everything much easier. So we passed to the experimental campaign, and this is thrust results for 3 different magnetic fields. And the main takeaways I would take from this is that the same trends that we identified with air are present here in terms of saturation when you increase the mass flow up to a certain point. And if you increase the magnetic field, the optimal value of the mass flow decreases, so the tendencies are exactly the same as with air, and even the 80% nitrogen, 20% oxygen, I get the same thrust as air. So this gives an answer to the question I posed before. Is representative in terms of trend, but not in terms of value, because you can see that if you increase the oxygen percentage, the thrust increases, and can pass from 0.8 that we saw before to almost 1.4. So this is important, but for the first stages of the design can be okay. And importantly, for the 900 Gauss, on all these black dots, I perform also current density measurements and ion energy distribution function measurements to gain some understanding of the physics there. So to tackle the problem of the ignition, I just added krypton to the mixtures, and there were different possible approaches, one more related with the physics of the discharge that consists on adding very small quantities that don't change the performance, but give you information about the physics of the discharge, or other more related with the performance that completely breaks the physics of the nitrogen and oxygen, but enhances the thrust. So we took a more or less intermediate approach, aiming to get the best thing of all of them. These are thrust results with the krypton mixtures, and I also took krypton thrust measurements, just only krypton without air, and very interestingly, the steps and the increases that you see there are exactly the same that you see without nitrogen and oxygen. And that tells us that the krypton is completely decoupled from the nitrogen and the oxygen, and is as if you had the air thrust and on top of that the krypton thrust without any interaction between them, what is unexpected and interesting, to be honest. So yeah, it enhances the performance. And last but not least, to tackle the problem of the plasma bloom composition, I decided to do optical emission spectroscopy. The one inside the source has already been performed. I'm still working on one just after the acceleration region to see if there's any difference. And I will also do one integrated line of sight inside the full source. And this is important because we had other possibilities, like using an E-cross-B that Borja designed, but nitrogen and oxygen are very difficult to differentiate there because of their similar masses. And I also did a plasma chemistry model with these kind of reactions that was more or less validated with the literature, aiming to do a global model, but we decided to abandon that or pause it indefinitely, let's say. What I will use it for is mainly to identify species and do qualitative analysis. I anticipated that I was going to be very short on time, so I had more slides that had to put to the backup in case anyone is interested in the physics and to see some reference spectrums that I had already taken. But now I will jump directly to the conclusions and say that all the work that I have been performing during this academic year has been focused on tackling these 4 specific topics that I identified in the beginning, both from the simulation part, developing a drag model, more or less complete, and during a very, very comprehensive experimental campaign with thrust measurements of more than 200 configurations and plasma plume measurements of more than 100 configurations, that if the air campaign was already the most comprehensive air-breathing helicon thruster campaign performed in the literature, this is even more comprehensive, so I guess it's better. And as future work, I complete the campaign. I hope to finish it in a few weeks. Modify the orbit propagation model to include the different gas mixtures now that we have the information. E-cross-B probe could be interesting, maybe even with the combination of the B-dot probe measurements that I took last year. So that would make it a very, very comprehensive campaign, very difficult to analyze and a monumental work, but probably one of the most comprehensive studies that are there for these thrusters. I will do a research state that is to be determined, the place and the scope, and the last activity will be to modify the device and analyze the performance changes. So we have one journal paper in internal review, hopefully coming soon. I participated in 3 conference papers, 2 international workshops, some dissemination activities, and also some teaching.